So here we continue with a derivative test involving trigonometric functions. So the function we have is f of x is equal to sine x plus cosine x, defined on the interval 0, including 0 all the way up to 2 pi. So the first step is to find the derivative and its critical numbers. So we have f prime of x is equal to derivative of sine x is cosine x, and derivative of cosine x is negative sine x. We set the derivative equal to 0 and solve for x. And that is going to give us the critical values, or the critical numbers. So cosine x minus sine x equals 0, which would imply cosine x is equal to sine x. Now, if you know trigonometric functions really well, we know cosine x is equal to sine x when x is equal to pi over 4, and we want to add pi to it because it is going to result in another period or another point. So pi over 4 plus pi, so we have pi over 4 and 5 pi over 4. We can also do this using the calculator. We have cosine x minus sine x, and we can graph it. Perhaps we can graph it between 0 and 2 pi. And we know that sine and cosine reach a maximum of 1 and a minimum of -1. And that is what we have. Now we can graph it, which we did, and we can trace to find the 0. I see 1 on the left side. And I get 0.78539, and if you did pi over 4, you'll get 0.78539. And we can graph it again, find the next 0, and we get 3.9269. And if I did 5 pi over 4, and I get 3.9269. So we know the two critical values. Now we simply have to find the minimum and the maximum. So we have 0 to pi. Pi is over here. So I would have pi over 4. And here I would, no, I'm just arbitrarily placing these points. We want to find a value between 0 and pi over 4 so that I end up getting a test point. So I'm going to pick pi over 8. And keep in mind, you have to plug this in the derivative and not the actual function itself. So cosine pi over 8 minus sine pi over 8. That gives me 0.5411, which is a positive number. So it's positive between 0 and pi over 4. Now I have to look at a point between pi over 4 and pi. So cosine pi over 2 minus sine pi over 2, which naturally is going to give me 0 minus 1, which is a negative number. And I have to find a number between pi and 5 pi over 4. I'm going to go for 5 pi over 8. I get a negative number because my test point is actually less than pi. So we want a number slightly over pi. So I have 5 over 4. Maybe I could do 4.5 pi over 4. That will lie between pi and 5 pi over 4. Still get a negative number, so it's slightly greater than pi, so we have negative, and 5 pi over 4 and 2 pi, let's see, how about 6 pi over 4, which is 3 pi over 2. That was a negative number. And 3 pi over 2 next. We know cosine 3 pi over 2 is 0. Sine 3 pi over 2 is negative 1. So we get 1, so that has to be a positive number. So the function is increasing, decreasing, decreasing, and increasing. So let's see if this picture holds true. So I am going to do sine x, the original function, sine x plus cosine x, and graph. And you can see that the function is decreasing, and so we have the point we had initially, which is at 2.339. And over here, it is at 6.283. So by looking at the graph, we can see that the minimum happens at 5 pi over 4, and the maximum happens at pi over 4. So I could draw this with a dotted line to sort of show you. So there's the maximum, and it decreases, gets to the minimum there, and it increases, and it ends up at 2 pi. So the local maximum is at pi over 4, and also at 2 pi. Excuse me. The local maximum is at pi over 4. The absolute maximum is at pi over 4. And x is equal to 2 pi. We can't call x is equal to 2 pi as a local maximum because that is an endpoint in this problem. The local minimum is at 5 pi over 4. Now we could find the point of inflection and identify the concavity. We sort of know by looking at the picture where the graph changes from concave up to concave down. So before we move on, I'd like to make a check here. 2 pi would actually give us 1. So we do actually have a maximum. Okay. The next step is to find the second derivative to identify the concavity of the function. So f double prime of x would be minus sine x minus cosine x. I'm taking the derivative over there. So we would like to have minus sine x minus cosine x equal to 0, which would imply minus sine x equals plus cosine x. So we want to know when cosine x, the positive value, equals negative sine x. So let's see where that would happen. This time I'll show you with a calculator. Then we can identify this directly. Minus sine x minus cosine x, and you graph. And that is what we get. So the 2 points here we can trace. And I get 2.35. 6. Now we want to write the answer in terms of pi. So what would 2.356 be equal to in terms of pi? So, oops. Forgot the number here. 2.3562. So we want to know what amount of pi would equal to 2.5362. So 2.5362 divided by pi, it gives us about 0.8. So 0.8 is simply 8 over 10, and 8 over 10 is simply 4 over 5. So let's say if sine 4 pi over 5 equals the negative of cosine 4 pi over 5. It does not, which means we made the wrong guess in finding the point of inflection to be 4 pi over 5, because this particular condition does not match. So how do we find the value? Let's go back here. .356. So let's try this again. 2.356 divided by pi would give you the amount of pi that would result in 3.356, and that gives me 0.7499, which seems like 0.75, so it has to be 3 pi over 4. So sine (3 pi over 4) is 0.707. Cosine 3 pi over 4 is negative 0.707, so that is satisfied. So what we have is x is equal to 3 pi over 4 is a solution. Now, we actually saw another zero crossing. So let's go and graph and trace to get the next zero. So it's right over there, and it's right over there, and I'm going to guess. I get 5.4977. So x amount of pi equals 5.4977. So we'd like to know what that x is. So 5.4977 divided by pi. The purpose here's to demonstrate how we can get the answer in terms of the pi's. So 5.4977 divided by pi gives us 1.7 pi. So, 7.5. So how do we get 1.75? We could simply add pi to this value. That would be 7 pi over 4. Let me do this again. So 1.748 is simply 1.75. So 1.75 is 1 plus 3 over 4. It is 7 pi over 4. Let's check that here. And we get 0.4977, and that is the value we had. So we could test it again. Cosine 7 pi over 4 is 0.7071, and sine 7 pi over 4 is minus 0.7077. So the next point is 7 pi over 4. I could have easily gotten this by doing 3 pi over 4 plus pi, which would give me 7 pi over 4. The reason why I'm doing it using the calculator is because you can sort of find the values in terms of pi if we know the calculator approach and make use of the calculator approach to get the answers in terms of pi. If you have difficulties identifying directly as to what the values are, just by looking at it. So we actually have two values now. And we are trying to find concavity, so the points of inflection are x is equal to 3 pi over 4 and x is equal to 7 pi over 4. So the domain is between 0 and 2 pi. I have 3 pi over 4, pi is over here, 7 pi over 4. We have to pick a number, easy number, between 0 and 3 pi over 4. I'm going to pick pi over 2. So if I pick pi over 2, I am going to get a second derivative of pi over 2, which is negative sine pi over 2 minus cosine pi over 2, which is negative 1. So since it is negative here, we would have concave down. We have to pick an easy number between 3 pi over 4 and 7 pi over 4, and that easy number is pi. It's right in the middle. So negative sine pi minus cosine pi. Negative 0, negative of negative 1 is positive 1. So we have a positive value here, so it has to be concave up. And between 7 pi over 4 and 2 pi, we need a number, so I'll simply pick 7.5 over 4, it's easier. So 7.5 pi divided by 4, I get a negative number. So negative number, so it is concave down. Oops, sorry. Now, if you look at the picture that I drew earlier, you can see the dotted green line follows the same pattern that I have up here. So the key here is to determine where the concavity changes. Don't confuse it with the pi over 4 and the 5 pi over 4 we found earlier. That tells you intervals where the function is increasing or decreasing. This tells you where the function is concave up or concave down. So the intervals where f of x is decreasing is all values of x that are in pi over 4 to 5 pi over 4. The intervals where f of x is increasing, so we have a bit here, right there, it's increasing, and right there, it is increasing. So we have 0 to pi over 4, union, 5 pi over 4 to 2 pi. The function is concave up for x in, so it is concave up for all values right here. So that would be 3 pi over 4, comma 7 pi over 4. And it is concave down for x in, I'll use a different color here, 0 to 3 pi over 4 and 7 pi over 4 to 2 pi or. So x in 0 to 3 pi over 4 union 7 pi over 4 to 2 pi. So I've shown you how to do this using the calculator and doing it manually. So we want the answers in terms of pi anytime we have sines and cosines. So if you can't recognize it directly, you could always make use of the calculator and use the process that I've demonstrated here to get the answer in terms of pi. So here we have another example, which is f of x is equal to x squared multiplied by ln of x. So the very first step is to find the first derivative. We have x squared times ln of x, so we have to use product rule. So u prime is 2x and v prime is 1 over x. U v prime, so x squared times 1 over x plus v u prime ln of x multiplied by 2x. So the x's would get cancelled. We have x plus ln of x multiplied by 2x. So we have to set f prime of x equal to 0 and solve for x. That would give us the critical number. So we have x multiplied by 1 plus 2 ln of x equals 0. Now, we want the values of x, so x would be equal to 0, or 1 plus 2 ln of x would equal to 0. So we know the first critical number, which is at 0. The second critical number is 2 ln of x is equal to minus 1. Ln of x would be equal to negative 1 over 2. X is equal to e raised negative 1 over 2. So those are, or I could write it as 1 over square root of e. So those are the critical values. 0 up to infinity, so because the domain is not specified. So 0 is over here. 1 over square root of e is over there. So I'm going to pick an easy number for x is equal to 0. Now keep in mind, at x is equal to 0, we actually will have a discontinuity because f prime of 0 would equal to 0 plus ln of 0 multiplied by, oh, I take that back. We won't have a discontinuity. That would result in 0. So pick an easy number between negative infinity and 0. So we will have negative 1 plus ln of negative 1 plus 2 times negative 1. But we can't take ln of a negative number. So that would become undefined. So I am going to pick an easy number between 0 and 1 over square root of e. Let's find out what 1 over square root of e is. So 1 divides by square root of e. It just puts e raised 1. I get 0.6066. So the test value that I can pick is 0.5. Let's plug in 0.5 and see what happens. So f prime of 0.5 would equal 0.5 plus ln of 0.5 multiplied by 2 times 1 over 2, which is 0.5, which is 0.5 plus ln of 0.5. And that gives us a negative number, which means the function is decreasing. Now I need to pick an easy number between 0.6066 and infinity. I'm going to pick 1. That is my test point, because ln of 1 would be 0, and it will make things easier. So 0.5 plus ln of 1 multiplied by 2 times 1, which is 0.5. I get a positive number, so it has to be increasing. So it seems like we can't plug in anything below 0, because if I plug in negative 1 or negative 2, I have natural logarithm of a negative value that will become undefined. So let's see if our graph matches what we concluded here. So we have to plug in the original function, which is x squared ln of, ln of x, and we graph. And you can see that the function is, adjust the window, is going of that sort. So the zero value that we found is, it's not the absolute maximum. So what we know is this particular graph satisfies the graph that I see in the calculator. So if you observe carefully, it sort of comes like that and it goes up. So what we have is the function is decreasing for x in 0 all the way up to 1 over square root of e, and the function is increasing for x in 1 over square root of e all the way up to infinity. Now, we could not have seen that particular dip, the minimum, without the aid of the first derivative test, which is why the first derivative test is quite important. So now that we've identified the critical value and the points of inflection, we can move on to, critical value and the intervals where the function is increasing or decreasing. We can move on to finding the points of inflection, for which we need to find the second derivative. We know the first derivative is x plus ln of x multiplied by 2x. So f double prime of x would equal to 1. We have to use product rule. U is ln of x, v is 2x, u prime is 1 over x, v prime is simply 2. So u v prime plus v u prime, and that would equal to 1 plus 2 ln of x plus 2. Now we set f prime or f double prime of x equal to 0 and solve for x, and that is going to give us the point of inflection. It's always good to have the graph of the original function to sort of get an idea as to what the function looks like. But you've got to keep in mind, sometimes there are points that your eyes cannot see, which is why we use the derivative tests to identify exactly where the minimum happens. So we're going to set this equal to 0 and see if the concavity changes. 1 plus 2 ln of x plus 1 equals 0. 2 ln of x plus 1/2 equals 0. Minus 1. Ln of x plus 1 is equal to minus 1 over 2. Ln of x would equal negative 3 over 2, which would mean x is e raised negative 3 over 2, which is 1 over e raised 3 over 2, which we can write it as 1 over square root of e cubed. And what is that value? That would be approximately equal to we get 0.2231. So even though I set the value of minimum here at -10, we know that this function cannot go below 0. So we start at 0 and we go all the way up to 0.2231 and the rest. So pick an easy number between 0 and 0.2231. Well, there isn't anything easy there, so I'm just going to pick 0.1. We have to plug 0.1 in the second derivative. So ln of 0.1 plus 1 times 2 and 1 plus 2 times ln of 0.1 plus 2, which gives us a positive number, which is 0.3948. So it is positive there, so it has to be concave up. Then we plug in an easy number greater than 0.221. So we will have 1 plus 2 times ln of 1 plus 1, which would give us 1 plus 2 times 1, which is 3. Still positive. So we have concave up there as well. So according to the second derivative test, the function is concave up for all values of x in 0 up to infinity. Is that true? Let's graph this. The original function is x squared ln of x, and if I graph, it's opening upward no matter what value of x that we pick from 0 to infinity, so our answer is in fact correct. So if you look at the graph, it's concave up. The green dotted line demonstrates that the function is concave up for all values of x. Here is an example involving exponentials. So the very first step is to find the derivative. We have f prime of x to be equal to e raised x minus e raised minus x. Second step, we have to set f prime of x equal to 0 and solve for x. I forgot to write where the local minimum is going to be in the previous problem. The local minimum, which in that problem is also the absolute minimum, is at x is equal to 1 over square root of e. So going back to this problem, we have f prime of x is equal to 0, which is e raised x, minus e raised minus x would be equal to 0, which would imply e raised x equals e raised minus x. That would mean e raised x equals 1 over e raised x, e raised 2x equals 1, and that could only happen when x is equal to 0. So there happens to be one critical value. Now we have to pick test points and plug it in. So my critical value is at 0. Now I'm going to pick test points, easy number, between infinity and 0. That would be 1. That is a test point. Easy number between negative infinity and 0. I'll pick negative 1. That's another test point. And plug it in the derivative, not the original function. So f prime of negative 1 is e raised negative 1 minus e raised negative of negative 1, e raised negative 1 minus e raised positive 1, which is simply e. So e raised negative 1 minus e raised positive 1, I end up getting a negative number. So we have a negative value on that interval. Pick an easy number, which we've picked to be 1. So e raised 1 minus e raised minus 1, which would simply be the reverse of what we had before. So this would be positive 2.35. So it's positive on that interval. So according to this graph, so the function, or according to the test, the function is decreasing on that interval, and the function is increasing on that interval. So what we can conclude is the point that we see at 0 is the absolute minimum, or the local minimum. So the local minimum is at x is equal to 0. Now, could that be the absolute minimum? Something tells me that it is the absolute minimum. So let's go ahead and graph this. E raised x, the original function, so e raised x plus e raised negative x, and graph. And you can see, as I mentioned, that value is in fact the absolute minimum also. And that follows, the graph of the function follows our deduction from the test. Now, even before we go on to the second derivative test, you should know the answer about concavity. This function is concave up for all values of x between negative infinity toward positive infinity. Let's see if that is true. So here, f of x is decreasing for x in negative infinity to 0, and f of x is increasing for x in 0 to positive infinity. Moving on to the second derivative, we have the first derivative to be e raised x minus e raised minus x. The second derivative is simply e raised x plus e raised minus x. We've got to set the second derivative equal to 0 and solve for x. So e raised x plus e raised minus x equals 0, which would imply e raised x is equal to minus e raised negative x. E raised x would equal to negative 1 over e raised x, which would imply e raised 2x is equal to negative 1. If you know your algebra, that particular equation is not true. Why? An exponential function is never negative. So here, a point of inflection doesn't exist. And clearly, the second derivative test failed to give us any information. So if we do not get a valid answer from the second derivative test, we can always go back and rely on the first derivative test. Remember earlier I wanted you to guess about the concavity, and we guessed directly by looking at the first derivative test that the function has to be open up for all values from negative infinity all the way up to positive infinity. So this would mean that the function is concave up for x in negative infinity all the way up to positive infinity. Here is another example that uses an algebraic function, which is x squared, and an exponential function, which is e raised minus x. So the process is very similar. First, we have to find the first derivative. It is the derivative of x squared e raised minus x. So u is x squared. V is e raised minus x, u prime is 2x, v prime is minus e raised minus x. U v prime, x squared times negative e raised minus x, plus v u prime, e raised minus x, multiplied by 2x. That is x squared minus e raised, times e raised minus x, which is negative x squared e raised minus x, plus 2x e raised minus x. We have an e raised minus x in common, so 2x minus x squared. Set f prime of x equal to 0 and solve for the critical values. So e raised minus x times 2x minus x squared equal to 0. And if you recall from algebra, an exponential function could never be equal to 0. So that factor cannot be equal to 0. That only implies 2x minus x squared equal to 0. If I multiply, or if I pull out an x, I have x times 2 minus x equal to 0, which would indicate x is 0 and 2 minus x is equal to 0. So the two values are x is equal to 0 and x is equal to 2. Those are the critical values. Now we perform the first derivative test. We don't have a domain, so we go from negative infinity all the way up to positive infinity. I have 0, I have 2. Those are the critical values. I need to pick test points. So I'm going to pick negative 1, 1/2, and 3. So f prime of negative 1 is e raised negative of negative 1 multiplied by 2 times negative 1 minus negative 1 squared, which is e raised 1 times negative 2, negative 1. We know an exponential is always positive. Sometimes you don't have to evaluate these values. You can sort of think about algebra and get to the sign of the function, because that's all we care about. So e is positive, negative 2, negative 1 is a negative number, so it has to be negative on that interval. Now we pick negative 1/2, positive 1/2. So e raised negative half, 2 times half minus 1/2 squared. An exponential is always positive. 2 times 1/2 is 1. 1/2 squared is 1/4. So I would have 3/4, which is a positive number. So I'm going to get a positive number. So positive. Function is decreasing here, increasing there. I'm going to plug in 3. So e raised negative 3 multiplied by 2 times 3 minus 3 squared. E raised negative 3 is always a positive number. I have 6 minus 9, which is a negative number. You see, I didn't even use the calculator because I only care about the signs. So I have a negative there, so it's decreasing. So what is our conclusion? The conclusion is the function is a decreasing for x in negative infinity to 0, union 3 to infinity. 2 to infinity. And the function is increasing for x in 0 to 2. If that is the case, if I sort of want to draw the curve, I could say the shape of the curve has to be, let's see, at 0 we have 0, so the function is going to come down, touch this, go up, and it's going to come down. Let's see if the graph matches what we have. The original function is x squared multiplied by e raised x. Going to graph that. And it's not obvious, but we've made a graph here, so let's see if that matches up. So we still have to do some adjusting here in the window. So let's do up to 2. And you can see that the function is decreasing, comes to 0, and then it's increasing. And past 3, it seems to go down according to our test. Maybe I made a mistake here. Let's see. Let's adjust the window. I stopped at 2. Let's go all the way up to 5 and see what happens. Well, it keeps on going up, which means we've made a mistake somewhere at 2. Easy number at 3. We have e raised minus 3 minus 3 squared. That is a negative number. Let's try this again. I just want to check and make sure that we did everything right. Most of it matches up except at 3. Let me adjust the window to make sure we're doing things right. I'm not hitting 3. And that's what we see at 3. So let me zoom in between 2 and 3, or 2.5 and 3.5. I don't see it decreasing. Let's adjust the window again to 1000. To 500. It seems like we've made a mistake. So give me just a second. By 2x minus x squared it is a negative number. So now let's move on to the second derivative, because our graph doesn't agree with our conclusion. So let's find the second derivative. The second derivative here is negative e raised negative x. Oh, sorry. E raised negative x multiplied by the derivative 2 minus 2x plus 2x minus x squared multiplied by negative e raised negative x. Let's see if we can simplify some terms. 2 e raised negative x minus 2x e raised negative x minus 2x e raised negative x plus x squared e raised negative x, which would give us e raised x's in common, 2 minus 4x plus x squared. And we have to set that equal to 0, and we solve for x. So we have e raised minus x, 2 minus 4x plus x squared equals 0. Clearly the exponent cannot be equal to 0, which would imply x squared minus 4x plus 2 equals 0. If we can factor, it is great, but unfortunately we cannot factor this. So x is minus b, we use the quadratic formula, plus or minus square root of b squared minus 4 times a times c divided by 2 times a. So we have 4 plus or minus 2 square root of 2 divided by 2, which is simply 2 plus or minus square root of 2. Which simply means that the 2 points of inflection are 2 plus root 2 and 2 minus root 2. So let's go ahead and put these points in. 2 minus root 2 is a positive number, and so is 2 plus root 2. So we have to pick an easy number between 0 and 2 minus root 2. I'm going to pick 0.25, which is 1/4, and plug it in the second derivative. So e raised negative x is going to be a positive number, so I'm just going to keep it as positive. Here 2 minus 4 times 1/4 plus 1/4 squared. So we have positive, and 2 minus 1 plus 1/4, and that would be a positive number also. So we have positive times positive, so on the interval negative infinity all the way up to 2 minus root 2, we have a positive number, so we have positive there. Between 0.586 and 3.414, we need an easy number. I'm going to pick 1. E raised negative 1 is always positive, and I would have 2 minus 4 plus 1. So we have a negative number. Easy number past 3.414, which is 4. So I'm going to plug in 4. The exponent is always positive. 2 minus 4 times 4 plus 4 squared, which is a positive number. So it seems like the function is concave up, then concave down, then concave up. And that is our conclusion. And that seems to agree with what the first derivative test is telling us. So the first derivative is in agreement with the second derivative. And when I graphed it, though, everything seems to be different. So, calculus does help you identify your mistakes. So what is the mistake that we made? Well, when I graphed, forgot to put that negative sign. So the moment I change that, everything falls in place. So I have a concave up part, a concave down part, and if we adjust the window a bit more, let's say to 4, and you can see there is another peak at 2, and then it turns concave up. So I could adjust the window a bit more, go all the way up to, say, 10. So there it is. So even if you made mistakes in graphing, you could always come back and rely on calculus to lead you to the correct answer. So what we did was perfectly fine. I did forget to include... Oh, I didn't. Okay. So what is our conclusion of the second derivative test? The function is concave up for negative infinity up to 0 union. The critical point that we found was 2 plus root 2, 2 plus root 2 up to positive infinity, and the function is concave down for 2 minus root 2 up to 2 plus root 2. So here is a slightly different problem that depends purely on a polynomial. And as always, the very first step is to find the first derivative. And we can use the chain rule. So we have 4 times x plus 1 raised 3 times 1 minus 5. Set the first derivative equal to 0. And solve for x. and that is going to give us our critical values. In the previous problem, the local minimum is at x is equal to 0, and the local maximum is at x is equal to 2. Sorry, I forgot to write that. Okay, moving on. So if we set 4 times x plus 1 cubed minus 5 equals 0, we will get 4 times x plus 1 cubed equals 5. X plus 1 cubed equals 5 over 4. X plus 1 is equal to the third root of 5 over 4. Five over 4 is 1.25. I get 1.0772, so 1.0772 minus 1, we get 0.0772. So that seems to be our critical value. The next step is to identify if that corresponds to a local minimum or maximum, whatnot. So 0.0772 is our critical value. And I'm going to pick a test point of 0 and a test point of 1. It's easy. We have to plug it in the first derivative. F prime of 0 would be 4 times 0 plus 1 cubed minus 5, which is 4 minus 5, negative 1, so it's decreasing on that interval up to the critical value. Pick an easy number, which is 1. 4 plus 1 plus 1 cubed minus 5, which is 32 minus 5. We get 27. Positive value, increasing. On that interval. So our conclusion is there is a local minimum at x is equal to 0.0772. The function is a decreasing for x in minus infinity all the way up to the third root of, well, I guess I'll put the decimal in, 0.0772, and increasing for x in 0.0772 up to infinity. Now, here is the fun part. We don't even have to find the second derivative. I actually know that the function is concave up for all values of x. But let's see if we get the same answer using the second derivative. So the first derivative is 4 times x plus 1 cubed minus 5. The second derivative is 12 times x plus 1 raised 4 times 1 minus 0, which is 12 times x plus 1 raised 4. And we have to set f double prime of x equal to 0 and solve for x. And that would give us the point of inflection. So 12 times x plus 1 raised 4 equals 0, which would imply x plus 1 raised 4 equals 0. That would imply x plus 1 equals 0, so x is negative 1. So that is the point of inflection, according to... Oh, I'm sorry, square. Bad math there. That must be square. So, negative 1 and 0 and 1. 0 would be my test point. And on this side, I'm going to pick negative 2 as my test point. So f double prime of negative 2 is going to be a positive number. Why? F double prime of x is 12 times x plus 1 squared. So no matter what number you plug in here, the second derivative is always going to be positive. So it's positive there, positive there, positive there, positive there, positive there. It's forever positive. So our conclusion, as the function is concave up for all values of x. Let's graph and verify if this is true. Now we came to this conclusion already using the first derivative test. The second derivative test agrees. Now, does our graph, or will our graph, agree with what we determined using the test? Hopefully it does. We have x plus 1 raised 4 minus 5x minus 1. I'll go from negative 10 to 10 graph. Looks like it. So what we did using the first derivative and the second derivative test agree with the graph. So everything is great. So here is another example on derivative tests. As always, the first step is to find the derivative. We have to use chain rule. So 1 over x squared plus 9 multiplied by 2x. Set f prime of x equal to 0 and solve for x. Two x over x squared plus 9 equals 0, which should imply 2x is 0, so x is 0. So our critical value is x is equal to 0. So I'm going to pick a test point to the left and to the right of the critical value. I'm going to pick easy numbers. So f prime of negative 1 is ln of negative 1 squared plus 9, which is ln of 10. I don't even have to evaluate this using the calculator because I know that natural logarithms are positive for x greater than 1, so I'd have a positive number here. F prime of 1 is ln of 1 plus 9. That would also be ln of 10. So it's positive here also. It seems like the function is increasing here and increasing there as well. Interesting. So the critical value seems to do nothing for us. Let's look at the second derivative. to see what's happening with this function. So the first derivative is 2x over x squared plus 9. The second derivative, we have to use quotient rule. U is 2x, v is x squared plus 9, u prime is 2, v prime is 2x. So f double prime of x is v u prime minus u v prime divided by x squared plus 9 squared, which is v squared. So 2x squared plus 18 minus 4x squared divided by x squared plus 9 squared. So we will have negative 2x squared plus 18 divided by x squared plus 9 squared. We set that equal to 0. And solve for x. And that would give us the inflection points. So minus 2x squared plus 18 divided by x squared plus 9 squared equals 0, which would imply minus 2x squared plus 18 equals 0. 2x squared would be equal to 18. X squared equals 9, which means x is equal to plus or minus 3. So the points of inflection happen to be plus or minus 3. I want to pick test points here, so I'm going to pick negative 4, 0 there, and positive 4. F double prime of negative 4 is negative 2 times negative 4 plus 18. The denominator is always going to be positive, so I'm going to have a positive number. It's negative 4 squared, which would give us negative 2 plus negative 32 plus 18 over a positive number, which would give me a negative number. So it's concave down. F double prime of 0 is 0 plus 18 over a positive number, which would give me a positive number. So it has to go up. And f double prime of positive 4 would be negative 2, 4 squared, plus 18 divided by a positive number. Which will be a negative number, so it's concave down. So it seems like there has to be a minimum somewhere here, which our first derivative test didn't find. It pretty much gave us 0 when we plugged in 0. I made the mistake that I should not have made. We should plug it in the derivative, not the original function. I keep advising you that, and I made the same mistake. So 2 times negative 1 divided by a positive number, which would be negative 2, and 2 times positive 1 divided by a positive number, which gives me positive 2. So negative. So it has to be decreasing, increasing. So of course I look at the second derivative and it gave me the idea that I did something wrong with the first derivative. So you can use both these tests together to come to a good conclusion about the function. So f of x is a decreasing for x in negative infinity to 0, increasing for x in 0 to infinity, concave up for x in minus 3 to 3, concave down for x in minus infinity to minus 3, union 3 to infinity, and the function has a local maximum minimum at x is equal to 0, because that is our critical number. So let's see if our graph agrees with what we did. ln of x squared plus 9, and window I'm going to set from minus 5 to plus 5, and graph. And looks like it is doing what we expected it to do. Let's adjust the window a bit. And we can see it clearly. So it's concave up. And then it's concave down. So we get a nice little picture, and that picture agrees with what we have. So here is an example where we have to find intervals where the function is increasing or decreasing. In addition, we want to determine its asymptotes. So first, let's determine f prime of x, which is 0 plus or minus 1 over x squared plus 2 over x cubed. Let's simplify this by taking the common denominator. So we will have 2 minus x over x cubed. Set f prime of x equal to 0 and solve for x. So 2 minus x over x cubed would equal to 0, which would imply 2 minus x is equal to 0. That would imply 2 is equal to x. So that is our critical value. Pick an easy number as a test point on the left-hand side. I'm going to pick 0. Right of the critical value, I'm going to pick 3. Plug it in the derivative. F prime of 0 is 2 minus, well, I can't plug in 0 because the denominator is x, so I'll have to pick 1. So that is positive, so the function is increasing. F prime of 3 will be a negative number, so it is decreasing, indicating that there is a local maximum at x is equal to 2. So f of x is increasing for x in we can write this at the end because this particular problem has asymptotes, so we've got to be careful. So let's give it a minute. Let's find the second derivative. F prime of x is minus 1 over x squared plus 2 over x cubed. So f double prime of x would equal 2 over x cubed minus 6 over x raised 4. Let's find a common denominator. So 2x over x raised 4 minus 6 over x raised 4. Two x minus 6 over x raised 4. Now we have to set that equal to 0 and solve for x. And that would give us the point of inflection. So 2x minus, set f double prime of x equal to 0. Which would imply 2x minus 6 is equal to 0, 2x is equal to 6, so x would be equal to 3. So the point of inflection is 3, so I'm going to pick an easy number on the left and easy number on the right. So my test point here would be 1, test point there would be 4. The denominator is positive no matter what number you plug in. So I would have 2 minus 6 over positive, which is a negative number, so it is concave down. The test point 4 would give me 2 times 4 minus 6 over a positive number, so it is concave up. Now we've got to be careful here because this particular function has asymptotes. It probably is going to have horizontal and vertical asymptotes. So recall f of x is equal to 1 plus 1 over x minus 1 over x squared. Find the common denominator, so we will have x over x, or x squared over x squared, plus x over x minus 1 over x squared. It's x over x squared, I'm sorry. So the common denominator is x squared, and we have x squared plus x minus 1. So the numerator is a polynomial of degree 2, the denominator is a polynomial of degree 2. So the horizontal asymptote is going to be 1. The leading coefficient here divided by the leading coefficient there. And clearly we have a vertical asymptote at 0, so The reason being, if I put in 0 in the function, the denominator would become 0 in 1 over x and minus 1 over x squared. So, key things to know. There is a vertical asymptote at x is equal to 0, which would imply that there is a discontinuity at x is equal to 0. And what we know is the function is concave down between 1 and, negative infinity all the way up to 3. So if it has to be concave down, it means that the function has to look something like this, concave down here, concave up there, because there is a discontinuity at 0, and it is concave down for all values less than 0, because there is an asymptote. And we also know that there is a horizontal asymptote at x is equal to, y equals 1. So probably it is of that sort there. And since there is an asymptote, and it is concave down, perhaps the function goes like this. Keep in mind, this is just our best guess scenario. Let's graph this and see how close we came. So 1 plus 1 over x minus 1 over x squared graph. And the only part that we made a mistake was right here. And the function seems to go that sort. I do want to zoom in because it seemed like I had some sort of concavity change at x is equal to 3. So perhaps if I zoom, I could get a better idea. So I'm going to go from -3 to +4 and change the minimum and maximum values from -2 to 2. So that part's okay, and that's what we get. It's 1 plus 1 over x minus 1 over x squared. I thought we had plus or minus 3. We simply have 3, so it makes perfect sense. So since we have an asymptote, over here we have it to be concave up. At 3, let's zoom a bit more. Has to be slightly over 1. So you can see that the curve is going up, and it's concave down, which is carried from that part all the way up to that part. But at about 3, the shape changes and the asymptote, it's going toward the asymptote. So it changes direction from concave up to concave down over here. So what we have is the function is concave down for negative infinity all the way up to 0, union 0 to 3, concave up for 3 to infinity. It's decreasing for x in negative infinity up to 0, increasing from 0 to 2, union, well, it's just 0 to 2, and it's decreasing again from 2 to infinity. So the important thing to notice here is anytime we have asymptotes, we need extra care. So in this case, it sort of is going like that and that way. Oh, sorry. It went up and plateaued again about 1. So you have to be careful anytime we have an asymptote. So it went up and goes like that. So it's no longer a guess. So what we have here is e raised negative x squared. And clearly this particular function would have asymptotes because we have exponentials. So when limit x approaches positive infinity, the exponent is a square, or x squared, so the power would always be positive, and e raised a negative positive number has to approach 0 as x approaches infinity. Now, even if I plug in negative infinity, I'll still have the same scenario because I'd have e raised negative of a negative number squared, which is positive. So I'd still end up having a negative exponent. So that would also approach 0. Now, let's perform the first derivative test. F prime of x would be e raised minus x squared times minus 2x because of chain rule. We set f prime of x equal to 0 and solve for x to get the critical number. So e raised minus x squared times minus 2x would equal 0. E raised negative x squared does not become 0 except in limit, so this would mean negative 2x is equal to 0, which would imply x is equal to 0. That is my critical value. So I'm going to pick a test point on the left-hand side, test point on the right-hand side. When I plug in a negative number in the derivative, have e raised minus of minus 1 squared multiplied by minus 2 times minus 1, which will be a positive number. So the function has to increase. When I plug in 1, I have e raised negative 1 squared, negative 2 times 1, which will be a negative number, so the function has to decrease. So it seems like f of x is increasing for x in minus infinity to 0. F of x is decreasing for x in 0 to infinity, and f of x has a local max, which in this case is also a global max or absolute max at x is equal to 0. Now we perform the second derivative test to determine concavity. So first derivative is e raised negative x squared times minus 2x. So we will have u as e raised minus x squared and v as 2x. V prime is 2. U prime is e raised minus x squared times minus 2x. So f double prime of x is u v prime 2 times e raised minus x squared plus vu prime 2x times minus 2x times e raised minus x squared. We have an e raised minus x squared in common, a 2 in common. So if we pull that out, we have 1 minus 2x squared. So we set f double prime of x is equal to 0 and solve for x, and that would give us the points of inflection. So 2 e raised minus x squared times 1 minus 2x squared would equal 0. The exponent part will never become 0, and it will only become 0 in limit. So we will have 1 minus 2x squared equal to 0. 1 would equal to 2x squared. This would mean x squared is equal to 1 over 2. X is equal to plus or minus 1 over square root of 2. Now we could perform the test minus 1 over square root of 2 plus 1 over square root of 2. My test points, I'm going to pick 0, 1 and minus 1. F double prime of negative 1 is 2 times e raised negative of negative 1 squared times 1 minus 2 times negative 1 squared, which will give us a negative number, which would mean it is concave down. Pick an easy number between negative 1 over square root of 2 and 1 over square root of 2. I'm going to pick 0, 2 e raised negative 0 squared times 1 minus 2 times 0 squared, and that is going to give us concave up. And pick an easy number, which is 1, 2 e raised minus 1 squared, 1 minus 2 times 1 squared, which will give me a negative number. It's going to be concave down. So f of x is concave up for values of x in negative 1 over square root of 2 and 1 over square root of 2. F of x is concave down for x in negative infinity to negative 1 over square root of 2, union 1 over square root of 2, all the way up to infinity. So if I have to guess this graph, there is a maximum up here, and it is concave up. So, and we also know that the function is increasing and it has an asymptote. So I'm thinking the function has to go like that and like that. And let's see if that is true. The maximum value of this function is going to be 1, so I'm going to set the window from -5 to 5. The minimum value is 0, maximum value 2, graph. And it seems like we did it right, so it is concave down, then concave up. And it is concave down again. So it's not very obvious by looking at the graph, but by doing the second derivative test, things become very clear. Here is an example of a rational function. So the denominator is not going to become 0 at all because it is a prime function. So we will not have any vertical asymptotes. But the function does have a horizontal asymptote because the numerator polynomial is of degree 2. The denominator polynomial is of degree 2. They are the same degree, they have the same degree, so the horizontal asymptote here would be y equals 1 over 1, which is 1. We can perform the first derivative test now. F prime of x, we have to use quotient rule. U is x squared minus 9. V is x squared plus 9. U prime is 2x. V prime is 2x. V U prime minus U V prime divided by V squared. Distribute and simplify 2x cubed plus 18x minus 2x cubed plus 18x divided by x squared plus 9 squared. That gives us 36x over x squared plus 9 squared. So we set f prime of x equal to 0 and solve for x. That will give us a critical value. So 36x divided by x squared plus 9 squared equals 0, which should imply 36x is equal to 0 because the denominator is not 0, so x would be equal to 0. Now we need to have test points. Pick an easy number. I'm going to pick -1 there, +1 there. F prime of -1 would be 36 times -1. The denominator is always a positive number, so I will end up getting a negative number, so the function is decreasing. F prime of +1 would equal to 36 times 1, denominator is always positive, I get a positive number, so the function is increasing. So f of x is increasing for x is equal to, or x in 0 to infinity. F of x is decreasing for x in minus infinity to 0, and f of x has a local min, which in this problem is also the absolute min for or at x is equal to 0. Now we perform the second derivative test. The first derivative is 36x over x squared plus 9 squared. So u is 36x, v is x squared plus 9 squared, u prime is 36, v prime is 2x squared plus 9 times 2x. I use chain rule and power rule, and that's what I would have. Now, f double prime of x is v u prime minus u v prime divided by v squared, which is x squared plus 9 squared, square it again. I have an x squared plus 9 in common in the numerator. If I pull that out, I have x squared plus 9 times 36 minus 144 x squared divided by x squared plus 9 raised 4. Cancel those two. I have 36x squared plus 144 minus 144 x squared divided by x squared plus 9 cubed. Now we set f double prime of x equals 0, and we solve for x. That would give us the point of or points of inflection. So we have 108x squared with a negative plus 144 divided by x squared plus 9 cubed. It's not 108, I'm sorry. Bad math there. Oh yeah, that is correct. Equals 0. I have a 36 in common. If I pull that out, I have negative 3x squared plus 4 equals 0. This would imply 3x squared, or negative 3x squared, plus 4 equals 0. X squared would equal to 4 over 3, which would mean x is plus or minus square root of 4 over 3. So our 2 points of inflection are square root of 4 over 3 and negative square root of 4 over 3. Pick an easy value between between negative square root of 4 over 3 and positive square root of 4 over 3. I'm going to pick 0. F double prime of 0. The denominator is always a positive number, so positive. And I'll simply have 144 in the numerator, so it's positive, so we'll have concave up there. Two over square root of 3 is the same as square root of 4 over 3, and perhaps I could pick a test point of negative 2 and positive 2 there. f double prime of negative 2 is negative 108, negative 2 squared plus 144 divided by a positive number always. Negative 108 times negative 2 squared is definitely less than 144, so we'll have a negative number over a positive number, so it will be negative here, concave down. Same would apply on the other side. Negative 108, 2 squared plus 144 divided by a positive number, which will give us a negative number. So it's concave down. So our conclusion is f of x is concave up for x in negative square root of 4 over 3 to square root of 4 over 3. And it is concave down for x in negative infinity up to negative square root of 4 over 3, union square root of 4 over 3 up to infinity. If I have to guess the graph, I know that there is an asymptote at x is equal to 1, and there is a minimum also, and it is concave up in the middle. So I'm thinking perhaps the graph it's y equals 1. Since there is a minimum, and when I plug in 0, I get minus 9 over 9, which is negative 1. So maybe the function is going like that. And it has an asymptote. And that satisfies the second derivative conditions that it's concave up for negative 4 over, square root of 4 over 3 and positive square root of 4 over 3 and concave down otherwise. Let's see if this is correct. Now that is just a guess. Of course, I could be wrong. We will see. And I'm coming up with that shape based on the inferences that I have from the first and second derivative tests. So x squared minus 9 divided by x squared plus 9. I'm going to graph it from negative 5 to positive 5, negative 2 to, it's not going to exceed 1, so I'm just going to put positive 2 and graph, and you can see that whatever guess that I made matches with the graph that we have. So I did great. So the first and second derivative tests are wonderful tools in identifying the shape of the graph and intervals where the function is decreasing or increasing, concavity, points of inflection, and critical values.